What's up, scholars? Today we're going to be talking about angular momentum and its conservation. And to begin, we're going to remind ourselves of some of the details about linear momentum, and then of course that's going to carry over into angular momentum. So the definition of linear momentum is P equals mv, that's the momentum is equal to the mass times the velocity, reminding ourselves that both momentum and velocity are vector quantities. So for angular momentum, we happen to use the capital letter L for angular momentum. And then what we need to do is think about the rotational equivalence of those quantities. So remember, rotational mass, we use the capital letter I for, and the linear quantity velocity, we're going to use the angular velocity omega, reminding ourselves again that these are both vector quantities, both angular momentum and angular velocity. For context, we're also going to add the units. They aren't very clean units for momentum or angular momentum. And the reason for that is that's not usually what we're calculating, but we should know those units. And we can work them out by looking at the individual quantities involved. So I'm going to do it with these little brackets. That'll be our little bit of unit analysis. So mass is in terms of kilograms, and velocity is in terms of meters per second. So that's the units for momentum, kilograms, meters per second. There's no fancy word like joules or newtons or anything like that. Now, if we look at the units, say this is the units for momentum or angular momentum, you'll hear me kind of shorten it to ang momentum, is, and it's a little tricky here, but if you recall, the units for moment of inertia are kilograms, meters squared, and then the unit for angular momentum is radians per second. Now, we've talked about this before, but radians aren't a real unit. They're sort of a placeholder. So even though this ends up being radians per second, we can kind of ignore the radians per second. So in reality, it just ends up being kilograms meters squared per second. So very similar, except for we've got an extra meter going on here in the angular momentum. So we are going to take a look at the conservation of linear momentum so that we can in a moment look at the conservation of angular. So very simply, the conservation of momentum says that whatever momentum you have at the start of your situation for however many objects in your system that you've got, it could be 2 things, it could be 3 things, it could be literally a million things. So we'll say P naught total, so the total momentum before the collision or the interaction, that's going to be equal to the final momentum, PF total, after the collision. Now, of course, we can fill in these details. Often we'll do things like having, P1 initial plus P2 initial equals P1 final plus P2 final. But keep in mind that we could have as many objects as we want. So you could have 2 cars collide or 2 balls collide, and this is how we typically do that. If we could take it one step further, usually we looked at something like M1 V1 initial plus M2 V2 initial equals M1 V final plus M2 V final. So we often looked at collisions between 2 objects. Now keep in mind we usually do this in 1 dimension, but this works in both 2 and 3 dimensions, each one of those being a vector in as many dimensions as you need. Which is to say that you all know how to solve this. You know how to get the information to solve this type of equation. For angular momentum, it's the same exact concept, except for instead of things bumping into each other in straight lines or at angles, for conservation of angular momentum, we have things spinning, and their momentum will be conserved as long as it's a closed system. So I should clarify, this is true for a closed system. That means there's no external forces. So here there are no external forces, and on this side there are no external torques. Okay? So So what will our equation look like? Well, we can just, again, directly translate this. The angular momentum will be L, the total angular momentum of your system that's rotating, whether that's an ice skater or a merry-go-round, whatever you'd like. And after the collision, so some kind of thing will change. Maybe the ice skater pulls their arms in, like you can see here. I printed off a little picture here. So we've got angular momentum before the, set in air quotes, collision. It's really just a change in their geometry. They're pulling their arms in. And afterwards, the idea is we're going to have the exact same amount of angular momentum, but it's possible, for example, that whereas you start with a large moment of inertia with the arms out, and they pull them in, they go to a smaller moment of inertia, but a larger angular velocity. We will take a look at those details momentarily. So finishing this off, it will look like this. The initial angular momentum of the entire system, the total angular momentum, at the beginning will be equal to the final total angular momentum. And again, we're assuming that this is a closed system with no external torques. So there's nothing, for example, like friction or air resistance causing a torque or applying a torque to this ice skater to slow them down. We're assuming they're the only thing in this system. So for the most part, we're just going to be looking at single solitary objects that have a moment of inertia before the collision or the interaction. So moment of inertia, we could say, is going to just be I omega, and we'll say it's the initial moment of inertia and the initial angular velocity. And at the end, we'll have some change to one or both of those things. So that is actually our bread and butter equation for angular momentum, keeping in mind that if there are more than one object, that we'll have to make some adjustments to this and have more terms in our equation. Many of you have seen someone, like in the Olympics, ice skating or diving, and what they'll tend to do is pull their arms in, as I showed, to speed up or slow themselves down. So I want to do an example of that where we're going to apply the conservation of angular momentum. I think that will make this all make it a lot more clear how to apply. All right, so I've done my very best to replicate this situation. I want to have this up here so it's a little more clear what's going on. The person starts with a large moment of inertia, and they're spinning relatively slowly. In this example, we're going to say that this ice skater is starting with a rotation rate of half a revolution per second, or 0.5 revolutions per second. Then they bring their arms in, and they are spinning at the end with a rate of 3 revolutions per second. They're really spinning much more quickly. We're going to say at the beginning, somehow we know that their moment of inertia was something like 4.6 kilograms meters squared. What we want to investigate here is what is their final moment of inertia. So we're going to apply a very straightforward version of this equation. So we're going to use conservation of angular momentum. I naught omega naught equals I final omega final. This is really just as simple as solving for the final moment of inertia. So that will be I naught omega naught over omega final. With one slight caveat. When we plug in information to equations like this, everything needs to be in SI units. So this needs to be converted to radians per second. So I'm going to just make a note, need in radians per second. The easiest way to do that is to remind ourselves that 2 pi radians is exactly equal to 1 revolution. I put 1 revolution on the bottom so that it will cancel with revolutions. And it's going to be the same conversion factor for the final angular velocity. Let me put hats on those. Whoops. So it's going to be multiply by 2 pi radians over 1 revolution. And we get, so you get pi radians per second and 6 pi radians per second respectively. That means they've sped up by a factor of 6. If you don't know those off the top of your head, those round to about 3.14 and 18.8 radians per second. So all you need to do then is plug this information into the equation, and we get the final moment of inertia. We should see it go down. Let's see if that's what we get. So the final moment of inertia is the initial 4.6 kilograms meters squared, and then that's going to be multiplied by the initial, which is just pi radians per second, divided by the final, which is 6 pi radians per second. It's actually really nice to see that, and this cancels out nicely. This is pi radians. We've got 6 pi radians, so the pi cancels. We're left with 1 over 6. So because their angular speed went up by, or angular velocity went up by a factor of 6, we can figure out directly that their moment of inertia must have gone down by exactly a factor of 6. So I'm going to write that out and then write the final answer. So if I simplify this, we get, I'm even going to say that these units cancel. So we get 4.6 kilograms meters squared times a factor of 1/6. And when we do that, we get 0.767, we can call it, kilograms meters squared. So there you have it, folks, an introduction to conservation of angular momentum and a very simple yet classic example. Thanks so much.